All right, so the last part of this chapter involves concepts dealing with geometric random variables. So geometric random variables are actually very similar to binomial random variables, which the first part of this section was about. And here are some examples. So like, let's say we have a pair of dice, six-sided dice, and we're going to roll them until we get doubles. That's going to be a geometric random setting. Think about why as I'm going through these. It's shoot a basketball from the three-point line until we make one. That's also going to be a geometric setting, or geometric random variable setting. And another one is keep placing a $1 bet on the number 15 in roulette until you win. So think about what the difference in these scenarios are when we're talking about them when they were binomial random settings. So you probably can kind of get down that what's going on here is that we're basically doing trials or trying a process until we get a success. See, so we're rolling the pair of dice until we get doubles, and then we stop. For binomial random variables, we're told how many times we're going to roll the die. Like we're told let's roll it 10 times and count the number of doubles. For like the basketball, for binomial random variable, we're told let's shoot the basketball 20 times from the three-point line and count how many times you make it. Here you just shoot it until you make it once and you stop. And the third scenario, we're placing $1 bet on number 15 until you win. With a binomial random variable, it will be like place it 20 times and count the number of times you win. So that slight difference is all that makes it a geometric random variable. Once you grasp that concept, you're going to find that problems dealing with geometric settings are actually pretty simple because they're actually like easier versions of binomial random variable problems. So let's look at the formal way we define it and talk about it in a problem. So say that we have a geometric random variable with a geometric distribution. If we're basically counting the number of trials it takes to get a success, and we use y, or large capital Y, to represent geometric random variables. We do that to distinguish it from binomial random variables, which are capital X. And so then we're still going to have probabilities P that are the same on each trial, just like in binomial random settings. And we're counting the values of Y that it takes until we get a success. The possible values of Y could be 1, 2, 3, 4, 5, 6. It could actually be, infinity, because maybe you never get a success. Maybe it takes thousands and thousands or millions of times to get a success. So let's go through a practice problem because that always helps to understand this stuff better. So let's say we have a pair of six-sided dice, your typical normal dice, and we're going to roll until we get doubles. So T is going to be the number of rolls it takes to get doubles. So you get a pair of ones, a pair of twos, a pair of threes, a pair of fours, a pair of fives. So how do we show this is a geometric random variable? So pretty much kind of like how we show that a variable would be a binomial random variable. We want to show, that, we have a clearly defined success and failures. So we want, it's binary, but again, I don't like to say that because it's geometric, the same sort of thing. Now we check that the probability of success in these trials is independent of any other trial, so it's not going to change based on your outcome on the previous trial. So like if you flip a coin and you get heads on the first flip, it's not going to change your chance of getting heads on the second flip. So we show it's independent, and we're basically counting the number of successes until we get, or counting the number of trials until we get a success. So that would make it a geometric random variable. And the die rolls are independent. The probability is always 1/6 of getting a doubles, and we're counting until we get a success. And let me not reveal too much. Give it away. Actually, let me sticky note here. All right, let's look at part B now. Let me work that out by hand. To find the probability of T is 3. Let's interpret what this means in context. All right, so probability of T is 3. Right, so the probability t is 3. So what is it? What are we trying to figure out here in context? So since we have a geometric setting, we're basically trying to find what's the chance that you're going to get a success on your third trial. So what's the chance that you're going to roll doubles on your third trial? So it essentially means, well, another way of doing this, the way you want to look at how we calculate this is that you have to figure out the probability of failing on your first roll times the probability of failing on your second roll and times the probability of succeeding on your third roll. So this would be like the probability of fail times the probability of fail times the probability of success. That's kind of the way you want to interpret this. Once you get this general concept down for geometric random variables, you're going to find that they're all the same and it's a simple multiplication. So what's going on here is that failing means that you don't get a doubles. So it means you get, anything else besides a pair of doubles. And since the probability of getting doubles is 1/6, so the probability of getting doubles is 1/6. So the probability of not getting doubles is going to be 1 minus 1/6 or 5/6. So the probability of failure is 5/6. So we basically do the probability of failing 5/6 times the probability of failing times 5/6 times the probability of succeeding, which will be 1/6, and that'll be our answer. 25 over 216. Looks like. About 11.5%. And what does that mean? Well, it's basically saying you have about 11.5% chance of getting your first doubles on your third roll. All right, part C. Monopoly. Probably all play that. A player can get out of jail by rolling doubles within 3 turns. I actually didn't know that. Anyways, I thought you said to pay. All right, but find the probability that this happens. So find the probability they'll roll doubles in 3 turns. So we want to find the probability that t is less than or equal to 3. The probability they can get doubles in 3 turns, 2 turns, or 1 turn. So those are the 3 possibilities that make this work. So then this would be equal to the probability that t is 1, plus the probability that t is 2, plus the probability that t is 3. Now, these are just calculated simply in the same sort of way that we did part B, but make sure you interpret them correctly. Remember, if we're find the probability that t is 1, that means you're going to get a success on your first roll. So we're just looking for the probability of a success. That would just be, 1/6. This would just be 1/6. So we have 1/6 plus the probability again doubles on your second roll, which means you're going to fail on your first roll. So 5/6 times 1/6 is fail the first roll and succeed on the second roll. Plus the probability t is 3, which we already found, but I'll just write it again just because. Plus 25 over 216. We do the math. We add all these up together. Again, 91 over 216. It's going to be about 42.16% or 42.13%. Now, that's really the main types of. That's really the main. These are really this problem pretty much covers the main concepts when you have the geometric random variable problems. It's really being able to identify. That's really what tests that these types of tests are going to be on. But there are formal formulas that you have you have in your formula packet. So let me just show them to you, and I'll briefly go over them. So turn to the next page. the geometric random variable probability formula is given as the probability that y equals k. So the probability of having a success on your k trial will be equal to 1 minus p to the k minus 1 power times p. Now, honestly, sometimes this makes these problems more complicated when you have to use these because you kind of overthink it. But let me just kind of briefly break it down. This part is just the probability of failing k minus 1 times, because the probability of succeeding is p, so the probability of failing is 1 minus p, and you're going to multiply that over and over the number of times until success. So if you're trying to find your success on a 10th roll, let's say, you're going to multiply this 9 times. So that's how we get a k minus 1. And it's going to be multiplied by p at that point, because that's going to be the success. Now, the mean of a geometric random variable is just going to be equal to 1 over the probability of a success. So 1 over p. We also say the expected value of y or the mean of y. So what this means is that this is what we would expect to be the number of trials that we would have to take to get a success. So like basically on average, we would expect this many trials before we get our first success. Now let's think about what this means, because it's actually pretty intuitive. So like and going back to the die problem, we're rolling a paired die. The probability of getting doubles is 1 out of 6. Let me go back to that. The probability of getting doubles is 1 out of 6. Let me use a sticky note. So we want to, let's say we want to find the mean of t. What's the mean of t? What the expected value of t in this scenario? I don't know why this mu symbols have been so weird. Well, let's think about this without having to plug and chug, because sometimes that makes these concepts more complicated. The mean of t, the expected value of t. Like, what is this asking for? What does this mean? What this is basically representing is that this will be the number of rolls we'll need to take usually before we get doubles. To get doubles, we have a 1 in 6 chance. So again, just kind of using your common intuition, if you have a 1 in 6 chance of getting doubles on any roll, that means on average, you'll probably need 6 rolls to get doubles. Now you know that sometimes you can get on your first roll or second roll or third roll, but on average, you'll need 6 rolls. Now, we can find this, with that formula if you need to. Remember, the p is 1/6, and the formula is 1 over p, so 1 over 1/6, and that's going to be 6. So again, that just means that on average, we'll need 6 rolls before we get a pair of doubles. So that's all that is. So don't overthink those formulas, because I learned that sometimes students overthink them, and sometimes honestly, showing them or using them kind of can make these problems more complicated or just weird. And last and not least, probably, because you probably want to use this, you can actually use your calculator to find geometric probability calculations. You can use them pretty similar to like what we did for the binomial random variable distributions. You have the probability that y will be equal to k, or the probability that y is going to be less than or equal to k. And you'll use a geometric PDF or CDF function. Probability density function, cumulative density function. So let's just kind of use a quick example with the problem we did again. So if you want to find the probability that t equals 3, we're going to go with the geometric random variable or geometric probability function, go into distributions. Remember, I got the old school calculator, so I'm going to have geometric PDF. I'm going to go to that. In the syntax, you only need 2 values. Remember, the number of trials you want until your first success and the probability, so PK. So instead of NPK, it'll just be PK, probability, and the number of trials for success. So PK. So I'm going to enter P first, which is, in this case, 1/6. Maybe I'll enter like let me put it in parentheses so it's exact. P is 1/6, and want to find the probability that of the first success being 3. So K is 3. Calculate that, and I see, and I get the 11.57% again. Same answer. Now the probability that T is less than or equal to 3, I can use the geometric CDF. Same thing, but this will calculate the probability that Y is less than or equal to K. In this case, like K is 3. Or in this case, 3 for part C. Probability that T is less than or equal to 3. Go back to the distribution functions. This time go down to geometric CDF and just go PK. So 1/6 is my P, and K will be 3. If you have like a more newer or recent version of a graphing calculator, it'll probably be easier. You won't have to memorize so much syntax. It'll probably just have a list. Anyways, I run this and see I get about 42% again. So that's just another way to do it. So use it as as you're doing these problems to save time, but make sure you don't use it to avoid, don't use them if you're not understanding what's going on, because that can be confusing. Use them just to save time. So I hope that helps.